Welcome back to Mastering C++ 20 Features. In this lecture, I will discuss how to create coroutines with co-yield keyword. But let's recap on what was taught in the last lecture. In the last lecture, I showed with examples how coroutines can be used as a freestanding function, a member function of a class, how they can be used as virtual functions in polymorphic class, how they can be used as lambda expression, and as static functions. Co-yield keyword has been introduced in C++ 20 and can only be used in context of coroutines. Co-yield keyword can be utilized to return intermediate values processed within the body of the coroutine, and coroutine can be suspended after the value has been evaluated with co-yield. The most common use case of coroutine with co-yield keyword are usage in sequence generators like odd, even, infinite, Fibonacci, etc., and usage as generators in range-based for loop. In this lecture, I will show how to create a simple finite sequence generator with co-yield keyword that suspends the coroutine after the value has been processed. Let's call this coroutine generator that takes in start, end, and step values as arguments, and as usual return the return object. Within the body of the generator coroutine, there is a simple for loop that iterates till the loop counter variable reaches the end value. And in the body of the for loop, we would like to return the loop counter variable to the caller of the coroutine and suspend the coroutine. To do this, we need a couple of steps. First step is very straightforward. You simply need to type co-yield val. That's it. But the second step is a bit complicated. Let's look at it in the next slide. To make the co-yield keyword work correctly with return object, the return object has to be modified slightly. Within the promise type, there has to be a method called yield_value. In the struct promise type, you can see the method named in bold. And if you also notice carefully, the method takes an argument which must match the type of the value that appears before the co-yield. In the case of the generator coroutine, it has to be an integer. And the method yield value returns a std suspend always awaiter. And this is exactly the awaiter that causes suspension of the coroutine after yielding the value and returning the execution control back to the caller of the coroutine. So in short, if there exists co-yield 5 within the coroutine body, compiler will call the method yield value with an argument 5. And this value could be saved within the coroutine handle and retrieved in the caller. Now let's take a look at a very simple implementation of the yield value method. First, the argument that is passed as a parameter to the method is saved in the member variable of the promise type. And next, the method returns std suspend always. And as I previously said, returning std suspend always allows the coroutine to suspend after yielding the value, which finally passes control back to the caller of the coroutine. And once the control is returned to the caller of the coroutine, the client code can access the value within the promise object member variable, which was assigned within the method yield value. Okay, let's see the generator coroutine with co-yield in action in a live demonstration. Here on top of the file, I have the same return object as in the previous lectures. If you notice on line number 6, the promise type struct has a member variable called val, just like I showed in the slides. In line number 7, the method yield value is declared, and in line number 20, a helper function to retrieve the val member within the promise type struct has been defined. It retrieves the val member by calling the promise method on the coroutine handle, which is also defined as a member variable within the return object. This returns the promise object, and we can directly access the member variable within the promise object and return it within this function. From line number 24 to line number 28, the generator coroutine is defined, which runs a for loop from start till end, and for every loop count, it co-yields the loop iterator variable. Right now, this code will not compile and run since the yield value method has not been defined completely. So let me define it right now here. Let's now use this coroutine in the main function. I'll run it from 0 to 10. Some bookkeeping variable. Now we access the value till the coroutine has finished execution. We'll print it on the console. And we should not forget to resume the coroutine. Now if I compile and run the program, we can see that the generator running the loop 10 times and yielding the value from 0 to 9. We can also try to use the generator as even and odd number generator by simply changing the start and step values. Let's first see the even number generator. For this, I need to change the step value to 2 at the point of call. So the default value was 1. I change it to 2. Now if I again compile and run the program, we can see all the even numbers between 0 and 10 printed on the console. Similarly, I can change this to an odd number generator by simply changing the start value from 0 to 1. If I compile and run the program, we can see all the odd numbers between 0 and 10 printed on the console. That was all for this lecture. I will upload this file and I encourage you to experiment with this code by using stdc out statements at various steps in the coroutine and promise object to solidify your understanding on execution control flow when co-yield is used in coroutine. Please feel free to ask any questions that you may have on the forum. Thank you and see you in the next lecture.